You need some sense.
Okay, so I think we're ready to start. All right.
Yeah. Sorry.
We got lots of people on Zoom and here. So welcome to the second part two of the Bayesian lectures.
First part two.
The first part, right? Take it away, Dave.
Okay. So last time we were talking about general issues in setting up Bayesian models, how to, how to set up priors, what a posterior is, and that sort of thing. Today, I want to talk about generally the next step, which is computing. So once you've set up a model, what are some ways that you can do computing? In particular, I'm going to be talking about Markov chain Monte Carlo. And then next week, we'll talk a little bit more about how to set up more interesting or complicated models. And I'm going to illustrate some of those sorts of models today in the context of computing, but they'll be kind of in the periphery, and we'll talk as we focus on the computing. Okay, so I have an example here. So these slides are designed for a little bit more of a mixed audience of statisticians and astronomers. So I'm going to not try to be the statistician explaining to you all what about astronomy, and skip over some of this a little bit about how stars evolve, and skip up to the more of the modeling bit. So this is a project that I've been working on for a number of years, where we are trying to model the evolution of stars in clusters. So we have the regular evolution of stars from a sun-like star to a red giant, and eventually a white dwarf. And we're going to be looking at a cluster of stars, and so we have photometric magnitudes for each of the stars in a cluster. And from that, we want to learn about the physical properties of the star. So why that works is, of course, as these physical properties shift, things like the mass and the composition of the star, the color changes in one way or another. So this is outlining how some of this works. More massive stars are denser, bluer, hotter, and burn their fuel more quickly. The composition of stars, metals tend to absorb blue light. Helium makes the nuclear reaction at the core of the star a little less efficient. And the spectrum, of course, changes as the star ages, as mass is converted into energy. So the composition changes, and via the mechanisms of the colors change. Some light is absorbed by interstellar material, and of course, more distant objects, including stars, are smaller and fainter. So, with that kind of science in mind about the relationship between the physical properties and the colors as they appear to us, we're going to, skipping to that third bullet there, we're going to use some computationally expensive physics-based computer models that essentially solve a set of coupled differential equations to make the actual link between the input physical parameters and what we expect to see in terms of the photometric magnitudes in a number of instrument-specific bands. We're going to be looking at clusters, and clusters are great from a scientific point of view, perhaps, but particularly from a statistical point of view, because the clusters all evolve together out of the same cloud, and that means that the stars in the cloud have the stars in the clusters have a lot of things in common. I say here the physical groups of stars formed together. The clusters have the same metallicity because they came from the same cloud, the same helium abundance for the same reason, the same age because they were formed at the same time, and they're physically together, say at the same distance, and the material between us and them is the same. And what that means is that instead of having on the order of 6 parameters for each star, I have only the mass for each star, and all these other parameters are in common. And that helps us avoid one of the trickiest problems in statistics, is when the number of parameters grows with the size of the data set, especially if the number of parameters is more or less equal to the size of the data set, you run into a lot of just challenges. Things become hard. Things like the central limit theorem don't work anymore. So this helps us out quite a bit. Only the initial masses vary. It becomes a bit more complicated than that. In some ways, what we're doing is, just as an aside, we're fitting a color magnitude diagram. Color magnitude diagrams this is a cartoon, but they're these fantastic things because you make this plot of comparing a magnitude and a color, and all the structure comes out with the main sequence down the middle and the red giants and the white dwarfs that have lots of physical interpretation. And an astronomer can look and say how many blue stars are left, and that tells you about the age because of the cluster, because blue stars are the first ones to turn into red giants or blow up and disappear. But what we're going to do essentially is we're kind of fitting a model to this, but we can use arbitrarily many, or at least reasonably more, photometric magnitudes, color filters. So we're because we're not just looking at the picture, we're using the pictures to guide us, but statistically we're using all of the data equally. And what the model looks like, we have these computer models that predict a number, maybe 5 or 6 color bands based on the mass of a particular star. So it's indexed by I because it's for a particular star. And that capital theta is going to capture all the other parameters that are cluster-wide parameters, like the distance and the age and the composition. And we build a likelihood where we have the actual observed photometric magnitude for each star in each filter and compare that with the predicted magnitude under the computer model as a function of the parameters. And the nature of the data is that a Gaussian model is reasonable. So that's our likelihood. And then we add some more bells and whistles. I don't want to dwell on this too much, but some stars are binaries, as you know. These are lovely pictures of binaries that you can separate. But those are kind of the easy ones. And the ones we're worried about, the ones that you cannot separate. So the light we see is the sum of the light from 2 stars that are presumably or possibly or most likely of 2 different masses. So we have to kind of, the predicted magnitudes becomes the sum, and they're log scales that we have to worry about because they're magnitudes. There's field stars in addition. This is a real color magnitude diagram. You can see the lovely main sequence and some white dwarfs, but there's a lot of other stuff around. So we have to be able to distinguish between the actual stars in the cluster and stars in the foreground or the background. So our likelihood becomes a bit more complicated. So where I used to have just the prediction for 1 star, I now have the sum of 2 stars. And I have to have another variable here that tells me Z is equal to 1 if it's a cluster member, and Z is equal to 0 if it's a background star. And I have to have a model for the magnitudes for the background. And that's not too important. It needs to be just kind of spread out and possibly everywhere. But it enables us to kind of probabilistically remove the background stars. So that's what the likelihood ends up looking like. We need prior distributions to give you an idea of what some of the prior distributions look like. An informative truncated Gaussian used for the log masses representing population distributions of stellar masses. So we know about this, what masses of stars generally are like, say, in our galaxy. And so we use that as our prior distribution for these particular stars in this particular cluster. The ratio of the smaller and the larger mass is uniform. You want to be careful about uniform priors, but using a few of them here and there sparingly is usually okay. For well-studied clusters, there's informative star by star priors, cluster membership, just on basic movements of the stars. Sometimes we have that, sometimes we don't. Mildly informative population priors used for the age. Again, we have some idea how old clusters are in our galaxy. We can have it doesn't have to be a flat distribution, but something that's roughly captures our expectations. And the remaining parameters are considered on a case-by-case basis. Maybe we have some spectroscopic data that we can learn about metallicity in a particular case, and that can lead to a nice informative prior. In other cases, we might not, and then we want to use something more diffuse. So the topic, so that's just building a model, basically, just an example. But the topic for today is how do we analyze that? And what we're going to do is we're going to generate a Monte Carlo sample from the posterior distribution. And this is an example. The reason I picked this example is because it has lots of kind of craziness in its posterior distributions. So this is a particular case where you can see if you compare age and mass, you get this kind of funny Z shape. Ted Van Hippel, my astronomy colleague, put this little plus on there because that's the posterior mean and standard deviations. Just to point out that posterior means and standard deviations mean absolutely nothing if you don't know you're looking at a bell-shaped distribution. Using this as your estimate would be quite silly, and these as your errors would be quite silly. So plotting these distributions is pretty fundamental. So those are really quite interesting. But even these sorts of high correlated, more or less linear distributions can be problematic. This is just a little picture, same thing. I'll bring a posterior distribution in 3 dimensions, so it's mass, distance, and age. And again, you can see these kind of complicated structures. This is for a very small data set. If you have bigger data sets, bigger clusters, these problems disappear. But
this is for a single cluster, or you have a distance as one of the axes.
yeah, so but that's an issue because so we would either there's a complicated answer to your first question, but the distance is the same in either case. So the stars in the cluster do have different distances, but on the for the most, if you're looking, unless you're looking at a cluster that's close to us, that the differential distance is not important. If you're looking at a closer cluster, then we have to play with it a little bit. In this particular case, this is just looking at a couple of white dwarfs. That's why you get this crazy posterior distribution. There's very little information. If you're looking at a full cluster with hundreds of stars, these distributions become much nicer. Oh, and this is a full distribution of lots of stars. And this illustrates these kind of multiple modes. These are the masses of, I picked the stars to pick for the picture, but 28 and 35 doesn't really, what those mean exactly. It's not clear, it's not relevant, but there's, again, the primary mass and the secondary mass, or the mass ratio, I guess. So you can compute the two masses of these stars. And what happens here is you get these multiple modes. If you trace it back, what you find out is, in some cases, there will be a star, if you go, maybe I can go back to this picture. Some of these stars are quite clearly background stars. But there's other stars that are close enough that they might be background or they might be cluster stars. And there's a certain probability that they're one or the other. And they're close enough that if you make it a cluster star, it actually shifts all the other parameters. Is that the discreteness in whether or not a star is a cluster star or not will shift the other parameters. In this case, the good thing is it's not shifting the cluster parameters, but it does start shifting some of the masses of other stars. But so the point, one of the points is that the multiple clusters, the multiple posterior distribution, multiple modes of the posterior distribution correspond to something quite physical in our understanding of the cluster. Maybe it's not in this case the most critical thing, if whether one star turns out to be a cluster star or not, but you can trace back the multiple modes to different stories about what's going on in your data. So generally speaking, when you see multiple modes, you don't want to do something like say, this mode's bigger, so I'm going to use this one instead of this one. You really want to kind of look and think about what those different modes might be telling you about the science. They're essentially correspond to different hypotheses about what's going on, and their relative probability tells you something about the relative likelihood of these different hypotheses. Here's another example. This example has nothing to do with astronomy. I always thought this posterior was really, really crazy. These are kind of okay, but these two here have these two tails that go out, and I chop it off, but these tails would go out into the parking lot. These long, tiny little, almost no probability tails. It's just a little weird, right? So all kinds of strange things can happen. It probably doesn't matter if you never knew about those tails, because there's not much probability in them, but it's still kind of strange and interesting. This is high energy astrophysics. This is pileup. We have two photons that arrive at your detector in the same time frame. You cannot distinguish them between two photons and one photon with energy that is equal to the sum of the energy. You just get the total energy. And so you have a spectrum that has, you can kind of see the spectrum here with these different modes. And what happens is you get these kind of, if you have two photons, and you know the sum of the two, and the distribution looks like this. If your one mode is 2, if one photon is 2 and the other one is 8, then they sum to 10. And also if one is 1 and the other one is 9, they sum to 10. So the structures kind of mirror each other, because you can't, one photon being 2 and the other one being 2, as long as they have the right sum, is exactly the same thing in terms of the data. So you get, again, these kind of strange structures. If you have 3 photons that have a fixed sum again with this pile up, you get this crazy posterior, these narrow kind of modes that look a little bit like 19th century tombstones in Harvard Harvard Yard. Okay, so those are like just trying to motivate you why we're interested in these kind of posterior distributions and what kinds of complexity can happen. Now I want to kind of shift gears a little bit and actually talk about how you do the analysis from a Markov chain Monte Carlo. This is a very simple example. We talked about it last time. Again, a posterior distribution for the background intensity and source intensity for a particular photon counting experiment. And you can get the posterior distribution, the marginal, the source intensity just by looking at the one dimension. Okay, so why is Monte Carlo such a powerful tool? It's essentially Monte Carlo, that is to say, getting a sample from a posterior distribution allows you to do integrals with ease. So this expression up top, that's like I for an arbitrary integral. If I'm interested in an integral of this form, where f is a density, if I obtain a sample from this density and just average the g of that function, this is an approximation of the integral. So instead of having to do the integral, I get a sample, and I just use that sample and averages from that sample. So if I want the posterior mean of theta, I just average these things. If I want the posterior variance of theta, I just take the variance of those things. So what started out as these kind of various integrals turns into just an exercise in computing summary statistics, means and variances of the sample and making plots. And if you want a 95% interval, you can just chop off 2.5%, the 2.5% biggest values and the 2.5% of the smallest values, and look at the interval that you have. So Monte Carlo makes, if you can get the sample, everything beyond that becomes quite easy. So our primary goal is to develop methods to obtain a sample from a distribution. The sample may be independent or dependent. Independent is better. Things, if you get an independent sample from a distribution, you get a lot more information than if you have some sort of dependent sample. Markov chains, we'll talk specifically, we'll define Markov chains shortly, but setting that aside for the moment, what they actually are. Markov chains can be used to develop the sample. So the technique is Monte Carlo. I want to get a sample from a distribution. If I obtain that sample via a Markov chain, that's Markov chain Monte Carlo. The base in Markov chains will give you a dependent sample, so there's things to worry about, be careful about. In a Bayesian context, we typically aim to sample from the posterior distribution. So I'm going to talk about, I think I'm going to skip rejection sample. You have this full set of slides, so you can look at these a little bit more later if you're interested, just to kind of focus on the main thing. These first two methods, rejection sampling, which I'm going to skip over, and the grid method, are relatively simple methods in low dimensions to get you a Monte Carlo sample, not Markov chain. The grid method is particularly simple, but it solves surprisingly many problems because it's kind of indestructible as long as you're working in relatively low dimensions. So imagine I have a crazy posterior distribution with, it's not Gaussian, some strange structured posterior distribution. It looks like that. What the grid method says is I'm just going to evaluate this thing on a grid. So it has a funny curve. If I can just evaluate it at the integers, in this case, up to 7, and then I compute the area of each of these trapezoids, which is not hard to do. And then I just sample from a multinomial distribution. So that means I find this area and I sample 1/2 with probability equal to this area, taking the areas and dividing them by the 1, so the probabilities. And I make it 1.1½ with probability equal to this area. So you can just kind of do it without any trouble at all, and you can make it arbitrarily precise by making your grid arbitrarily fine. And in most cases, anything near this is going to be far more precision than you really need. The trick is that it really falls flat if you get beyond 3 dimensions. Even 3 dimensions, this becomes a lot of work. If instead of evaluating in 1 dimension, if I have to evaluate on a plane or in 3 dimensions or more than that, it becomes quite tricky. But as we'll see, there's lots of ways that we have where you can kind of separate a problem into bits. So maybe you can deal with all the parameters but one, with a standard simple method, but there's one parameter that doesn't work, and you might be able to use the grid method to handle that one parameter, for example. So it's a pretty handy thing to have in your back pocket, even though it's kind of ridiculously simple. Okay, so let's go on to Markov chain Monte Carlo, the kind of the real deal. So what is a Markov chain? Markov chain is a sequence of random variables where if I tell you the whole, you have a kind of a history. If I tell you the whole history and you want to find the distribution of the next object, it depends only on the most recent one. So the simplest example of this is a random walk. I take random steps either to the left or the right over time with certain probabilities. Well, where I end up at the next time point depends only on where I am now, because I'm just taking random steps from where I am right now. Where I've been in the past makes no difference. Okay, so that's a Markov chain. Markov chains, what we're particularly interested in this thing called the stationary distribution. And what the stationary distribution says is if I have if I know the distribution of the chain at time t-1, so the previous step, and I know how it progresses, the distribution of how it goes from the current value to the next value. So this is a marginal distribution. This is a conditional distribution. So I multiply them together, I get the joint distribution of the previous step and the current step. And then I find the marginal distribution of the next step, and these are exactly the same. Stationary distribution. So that means if I have a draw from the stationary distribution, and I proceed one step via of the Markov chain rule, I get another draw from the same distribution. And that's why it's called a stationary distribution. If I'm there, I stay there, and I can get arbitrarily many draws from the same distribution. So if I have a sample from the stationary distribution and do a Markov chain update, then the next iterate follows the same distribution. So for what our goal is going to be is to find distributions, a jumping rule, the Markov chain rule from going to the current value to the next value, such that the stationary distribution is our posterior distribution that we want to sample from. And if we can find that a jumping rule so that our posterior distribution is the stationary distribution, that means if I can get one draw from that distribution, just one, I can get as many as I want. Okay. In practice, unfortunately, even one is hard. But if I could get just one, I'd be done. Okay, and this part's a little more technical. In a bit, I'll get to like some more illustrative things, but I just want to give you a kind of a bird's eye view of kind of how the theory of these things work. What does a Markov chain at stationarity deliver? Well, if this thing is my the distribution I actually want, the posterior distribution. I'm sorry, the posterior distribution or the stationary distribution. The Markov chain, so the conditional distribution of the current draw given the starting value, if I run that chain long enough, the effect of the starting distribution disappears. Okay, so you can see here, this is if I have my random walk again, if I start here and I take, 2 steps, I can either, or maybe I take, 1 step this way or 1 step this way. I'm not going to get very far from where I started. And if the whole stationary distribution is the whole room, the fact that I started here, or if I start there, is going to matter where I am 2 steps later. I'm not going to get all the way around the room in 2 steps. But if it's not 2 steps, if it's 1,000 steps or 100,000 steps, where I started doesn't matter. The effect of the starting value disappears as I run the chain longer and longer. And that's all this is saying. And it's also, and this other bit is saying that if I average the draws from the Markov chain, like I wanted to for the Monte Carlo sample, if I do that, it also converges to the expectation, if I sample the thetas from the Markov chain, that converges also to the mean, the posterior mean. If I get more and more samples. So what we usually do in practice is after a sufficient burn-in time, we have a Markov chain, we've run it for capital N iterations. We throw away the beginning of it and then pretend like, or, you know, act as though we have samples from the stationary distribution. And I'm saying pretend because it's one of these things it's mathematical convergence, right? It's asymptoting. You never quite get there. But once you're close enough, you don't worry about it. You chop it off and you pretend you're all there. And so, you know, there's where we're talking quite a bit about convergence diagnostics to make sure we're doing that in a reasonable way. Okay, so this is a little more concrete, hopefully. How do these things actually work? How do I build a Markov chain Monte Carlo? The simplest one is called the metropolis sampler. So I draw theta from some starting distribution. So I just get a starting value somehow. And then for every iteration, what I do is I do something, I go from where I am, I have a conditional distribution from where I am to the next value. So that might be just a normal distribution or a random walk kind of distribution. So where I am now, I have a distribution for where I go next. I might just take my current value and add a normal variable with standard deviation 1 or standard deviation 10. Go left and right, left and right. But if that's not enough, because that's just a random walk. Why would I think that's what does that have to do with my posterior distribution? So to make it work, I have to compute this ratio where this is my target distribution, my posterior distribution. I'm going to compare my current value with the proposal. And the rule essentially says that so I have a distribution that looks like this. If I step towards the mode, if I end up a place higher on the posterior distribution, I grab it. If I end up on a place lower than the posterior distribution, I'm going to accept it with a certain probability. And that probability is this ratio. So if this ratio, so maybe we shouldn't worry about the mathematics, but you can make a connection with the mathematics with what I just said, right? If you're going up, if this ratio is bigger than 1, you're up. So the probability is going to be 1. If this ratio is less than 1, then I'm going to accept it with probability R, which is some number less than 1. So if I'm here on the posterior and I go down to a value that's half as high, I'm going to accept that with probability 1/2. Okay, and if I don't accept it, I stay where I am for another iteration. Okay. The only thing that you need to have, the only rule here is that this thing has to be a symmetric rule, which means if I'm here, the probability that I go here is exactly the same as if I started here and went there. So adding that normal error does that. A normal error, a normal distribution is a symmetric distribution. Okay, so let's see what it actually looks like. So this is that funny distribution that I had before.
Show this symmetry.
Yeah.
Sometimes we take logarithms of the parameters. If your proposal then is symmetric in the log, it will be symmetric in.
Yeah, you couldn't use it. It won't work.
Yeah.
Yeah, you have to. There'll be you would have to have a jump with this algorithm. There's other algorithms, but with this algorithm, you'd have if you're working on the log scale, then it has to be symmetric on the log scale. So I mean, and that the issue comes up in if theta is just theta, and I instead want to compute the logarithm of theta, call it phi, then these two things are going to change. And so this ratio will be different. And so to get everything back into balance, you need to have a distribution that's on the log scale symmetric.
So basically, you've got to work with log parameters.
Yep.
Use log parameters.
Throughout. When I do it, when I take a logarithm, when I'm doing the math or even writing a paper in the astronomy journal, if I started with mass and I want to work with log mass, I say theta equals log m, and then I forget m ever existed. just because it just keeps you grounded on what scale you're working on. And then at the end, when you're all done, then you can exponentiate and get the masses back, but. Okay, so let's this distribution here. So one of the key questions is going to be, so this is my current value, and I'm going to get a normal distribution, which means for my current value, I'm going to sample from, this is a very tall normal distribution. And suppose I go from here to here, then I'm going to recenter that normal distribution here and sample again. One of the questions is going to be, how big should that normal distribution, how wide should that normal distribution be? So here I have a narrow one, and here I have I guess there's 4 of them, there are varying widths. And how, and that's going to determine how big my jumps are going to be. So in some sense, these are much nicer, right? Because if I go here, I might jump all the way over here. Whereas this narrow one, I'm not going to jump very far. So what is the preference? So there's some details here I'm kind of skipping over. Normal distributions, you can do a few flat distributions, also symmetric. A T distribution is a normal distribution with fatter tails, but still it's a nice symmetric bell-shaped distribution. So let's look at an actual example. So this is a simplified model from high energy physics. I have 1,000 energy bins. I have a power law. I have data that follow a Poisson distribution. This E is the energy for the bin. So the energies are, in a nice grid of values between 0.3 and 7. These are the 2 parameters I'm interested in, alpha and beta. I'm going to use uniform distributions on those 2 parameters. And I'm going to, so that gives me a model. I can write down the likelihood. I have a prior distribution that I can get the posterior distribution. And I'm going to use a metropolis rule with a Gaussian jumping rule. So I'm going to have, just like on the previous slide, I'm going to have my normal distribution is centered on the current value. And I'm going to have standard deviation. I don't know why, but I have 0.08. That's my standard deviation. And the correlation is 0. So now I've kind of jumped a little bit. In all my pictures, I had 1 dimension. Now I have 2 dimensions, but that doesn't really complicate things very much. Now I can take a random walk and a circle around me, and that's going to have a bivariate Gaussian distribution. You can imagine that I have a correlated bivariate Gaussian distribution where I don't step that way. I only step in this direction. I know my posterior goes in that direction. That might be a useful thing to do. In this case, I don't know anything, so I'm going to just say the correlation is 0. That's a data set. Not very interesting. But you can see the true values there, which we'll compare our answer, what we get with. This is a time series plot of the metropolis draws. And so the alpha is at the top. That's the normalization parameter, and the power law parameter is beta at the bottom. You can see I purposely, I know the truth in this case. I purposely started a little way away from the truth. Can't remember the truth anymore. Was it 1.8 for beta? 1.69, we'll call that 1.7. So the truth is, here. I started up here, and the chain kind of meanders down, takes it a few iterations. The other thing you can see is it gets stuck. Just sticks to the same value for a little while. And what's going on there is I'm proposing and rejecting, proposing and rejecting, proposing and rejecting. So when that happens, I stay in the same place. Okay, and the same thing is happening with alpha. And so even though I have 500 iterations, there's not 500 unique values. That's the joint posterior distribution, a beautiful Gaussian distribution. These are the marginal distributions of the normalization. This thing is called an autocorrelation plot. And what that does is you're looking at your chain, and the first value is the correlation of the current value with the current value. So at least the way that this particular software does things, the first one should always be 1. And then the second one is the correlation, the 1-step correlation, the correlation of the current value with the previous value. So you just take your full chain, shift it by 1 iteration, and then compute the correlation coefficient. You don't have to do that, but that's what the software is. And then you can see the correlations are coming down when you get to lag 40. It doesn't ever quite get to 0, which is a little disconcerting. But the answers don't look too bad. This is the histogram of the posterior distribution. This is just the curve is just a smooth version. The true value. I remember the other parameter, 1.7. This one is 5. So you can see the true value is here. The posterior distribution is not centered right on the truth. That's okay, right? Because just when you estimate a parameter, you don't expect to get the true value out every time. If you did that, you wouldn't need statistics. But the width of this distribution is giving you, it's supposed to say, this is how big my errors are likely to be. And the fact that it's in that distribution means we're fine. If you do this thing, if you test your algorithm lots of times and you're always way over on the right, you think something's probably wrong. Yes, I'm kind of biased. But if the thing's kind of moving around the distribution, sometimes too big, sometimes too small, sometimes right on, that's exactly what you'd like. And so I can compute the confidence intervals. I just 95% again, I just chop off 2.5% here, 2.5% here, and that's the interval that I get. That's alpha, beta, same story, except beta looks a lot better. This is what you like. If you see this, you're like happy, nothing to worry about. My chain is doing exactly what I'd like. Okay, the other one's not crazy. I've seen far worse, but this is really good. Okay, Metropolis Hastings. It's exactly the same as Metropolis, except it works in Vinay's case. So now I can have a more generic jumping rule. J, the jumping rule, J, can be any jumping rule. It doesn't have to be symmetric anymore. The price for that is that the way you compute R used to be just this, because when this is a symmetric distribution, these two things are equal, it disappears. So the acceptance probability becomes a bit more complicated, but you can use any rule you want. So one thing that people sometimes do is called the independence sampler. Not independent. It's close. Essentially, what you're going to do is you're going to have a jumping rule that doesn't depend on the current value. So one thing you might do is you might make an approximation to the posterior distribution. Maybe you can just find the mode with an optimizer, compute the curvature, and make a Gaussian approximation. And you just always jump from that distribution. It's the same distribution every time. That's not symmetric with regard to where you are, because it's always the same regardless of where you are. But it's a different strategy that might work. So this is, you might use a normal distribution with a map estimate. So you have to do like optimization and lots of standard software to do that. Compute the variance by taking second derivatives. That's a little harder, but lots of optimization have to do this anyway, so they can just spit it out if you have a kind of a derivatives-based optimizer. This is just normal, doing a normal approximation like that might not be perfect, right? This is just some kind of skewed distributions in the normal approximations. But you're hoping that the algorithm kind of corrects this for you. If I would be careful in a case like this, right? Because if I'm always jumping from this distribution, and this is the truth, I'm not, this is essentially zero. I'm not going to get the values I need here. So if you have a rule like this, what you really want is make it a little too wide. Take this variance and triple it. So you get some values down here. Having a little rejection, having rejection is fine. Not getting to parts of your parameter space is problematic. So this is, I won't go through the details. This is going back to the same example I had a moment ago, which is the power law model. And it's showing you in R, because how you can compute the optimal value and the variance and all that to get the normal approximation. So you probably don't need to know those kind of details, but I can compute that normal approximation. And because in this case, we know the normal approximation, remember this, the normal approximation is probably pretty good, because you should plot contours and things to really know, but because we know about the central limit theorem, we have a lot of data, it looks like that, probably the normal approximation is pretty good, and it turns out it is. So this is the independent sampler, and you can see I started far away, but remember the proposal doesn't depend on the current value, it just samples from this approximation. So it immediately jumps to the posterior distribution, and these two things sample quite nicely. There's almost no sticking. I accept 99% of the time. 1 in 100 draws I have to toss because the normal approximation isn't quite right. But I'm essentially correcting that normal approximation. So that works quite nicely here. Now look at alpha. Look at that. So I said this looks good. When I say that, just to make sure you understand, when I say this looks good, it's because these correlations fall off to zero very quickly. You have close to an independent sample. Now look at when I use my independence sampler. They're essentially zero immediately. These are, if they're within the dashed lines in this particular plot, they're essentially null. So you get, Fantastic result in this case, and for the beta as well. Okay. Yeah.
So what determines the autocorrelation then? So what's the, I guess it's the probability distribution or the chance distribution?
Yeah. Yes. So, I mean, we will definitely talk about that. That the next one of the next topics is to talk about in the context of the metropolis sampler. So if you go back here, where's that nice picture here? Each of these different proposal distributions will have a different effective autocorrelation. Yeah, that, you know, I don't, the independent, I mean, that problem that I just showed, this problem is really designed for an independent sampler. Independent samplers is not like some magic bullet. But if you have a lovely posterior distribution that looks like a Gaussian and you can compute that Gaussian, well, it works pretty well. But, you know, those aren't the problems we're really interested in. I don't want to oversell the independent sampler. It works really well because it's a particularly easy problem. But yeah, so we're going to come to that. Really, that's the next topic. Yeah. I think I'll just leave this for you. This is, you know, Markov chains converge to stationarity. When, why, how, mathematics. Ergodic theorems. It's quite, you know, if you really want to get into this stuff, it's quite detailed. This is meant to just be, you know, kind of an overview. It turns out that at the end of the day, if you have a Markov chain that has 3 properties, it will work. Maybe, you know, it will work in infinite time. Sometimes they're very slow, but it will work. The first is irreducible, and that's well, essentially what irreducible means is that anywhere I am in the parameter space, I have positive probability of getting anywhere else. So somehow I don't say if I land here in the posterior distribution, I can't get here. Clearly, that would be a problem, right? So you have to be able to move everywhere. So these are very simple, both of them. Aperiodic just means that I can only be in this value of the parameter space on even numbered draws or on draws that are divisible by 5. If it's something very strange like that, that's going to be problematic. Don't do something like that. And then the posterior distribution is the stationary distribution. Well, that's what we already described. So if you're interested in the mathematics, this is a good place to just get kind of some of the keywords. But, you know, it's not that important for figuring out how to run these things. So practical challenges and advice. So convergence diagnostics, choosing the jumping rule is what we were talking about just a moment ago. So probably the biggest, there's 2, you know, you think about, there's kind of 2 things we want to think about. One is that, have we run the chain long enough to use that these asymptotic, you know, results are going to give us the right answer? And then the next question is, can we build a more efficient chain? The first question is most important, you know, because you want to make sure what you're doing is correct. The fact that you could do it more quickly, that's it's good, great, we'd like that, but it's kind of secondary importance. So the first question I want to ask is, how do we know the chain is doing the right thing? So you often will see this sort of a pattern in a Markov chain, where, you know, it starts over here and it kind of works its way to something else, and then it kind of looks fine. And you can kind of look at the thing and you say, well, I need to chop off the starting values. I mean, you don't really have to, in theory, you don't have to, if you look at the theory, you don't have to chop off the starting values, because if you instead of running this thing, it's asymptotic results. Asymptotic results have, you know, they're nice mathematically, but they're a little silly. If instead of running this thing at 500, if I run it 5 million iterations, this will disappear. Like, it just isn't important anymore. But in practice, instead of running the thing 5 million iterations, you can chop this part off, and then 500 are enough. Right. So often what you do is you kind of look at the thing, look for a place where it looks stationary, and chop it off. That's like you're getting rid of the burn-in. So this is the question here is, has this chain converged? Is it okay if I chop it off at, say, 100? Well, one thing you probably want to check is just run it again with a different starting value, different random seeds, this sort of stuff. And this is a really nice, kind of famous example. It's, you know, 30 years old now, but when people were first discovering this stuff and saying, you know, like, you need to be careful is what this is saying. Because this is exactly the same Markov chain, exactly the same problem. And you can see that, has it converged? Well, if I looked at just the one, I thought I was golden. But when I look at the two, if I look at either one of these by themselves, it looks golden. But they tell me something different. And probably what's happening here is that the posterior actually has two modes, and the chain sometimes goes to one and sometimes goes to the other. If that's the case, now you want to say which of these, is this mode 90% and this mode 10%? Are they 50-50? Maybe this one's 99.9%, and this only happens one time in 1,000. If that's the case, well, then you can probably throw away the one that's only one time in 1,000. But you need to ask those questions and look more closely. And if you just run one chain, you might never know there's an issue. Here's another example that I ran across myself some time ago. And those first two chains, actually, the first two chains are right in this case. It's just that the third chain looked fine for a very long time. It's a little funny, it's a little wobbly, but it's kind of okay. But then it just, changes its mind, whoop, and goes over to the real posterior distribution. So you get lots of strange things. So comparing results with multiple chains, check convergence. So start the chain from distant points in the parameter space. So like kind of far away and maybe semi-unreasonable values. In a scientific question, you have some idea what is the age of stars. We'll make the really extremely old age and a really extremely young age, and then see if they come together and in the middle. Run until they appear to give similar results, or they find different modes. They may never give you similar results if you really have multiple modes. Again, this is a standard statistic. And maybe I'll go over this quite quickly. This is the Gelman-Reumann R-hat statistic. And what this is, what does it mean for them to give you the same answer? So I have these draws, psi and m. So I've run m chains, and the little m is indexing the chain. So maybe there's 5 chains, say 1, 2, 3, 4, 5. And I run each of the chains maybe for 1,000. So n goes to 1,000. So these are, the psi's are the draws from all the chains and all the iterations. And then what I'm going to do is I'm going to kind of essentially compare the within chain. What do I get from a single chain? And what do I get from multiple chains? So this B is for between. So it's computing the average for each of those 5 of these, in the way I just described it. And I compute the variability of the means. And I compute the within chain variance. So that just means I compute the variance of each of the chains and average them. That's the within chain. And then I essentially think because I'm starting from far away bits of the parameter space, the chains start out far away and they come together. So especially this between chain estimate should start out being an overestimate. And then as the chains run, they come together and that variance gets smaller. Okay. On the other hand, the within chain estimates tend to be underestimates. And that's because if I have a high correlation, if I have a chain that's doing this, it's kind of just moving around the parameter space. But if I start by looking at just this bit, it hasn't reached all the bits of the parameter space, so it's underestimating the variance. So I have an underestimate and an overestimate, and when they agree, when the ratio becomes close to 1, then I say that the chains have converged. And this thing, again, any standard Markov chain Monte Carlo software will compute this thing automatically for you. But it's again, the way to just understand what it's doing is just trying to make sure those chains are in agreement. Okay, so let's look at some questions on efficiency. Again, this is going back to that power law Poisson model. And this is for alpha, I think. The power law parameter, so it's the beta, the power law parameter. And now I've run the chain, the metropolis chain 3 different times with still Gaussian jumping rules. But last time I picked a particular standard deviation. Now I'm comparing 3 standard deviations. This is 0.005, 0.08, and 0.4. So this one I'm taking big jumps, relatively speaking. This one I'm taking tiny little jumps. And what happens is when I take tiny little jumps, I almost always accept. I'm not moving very far. But it takes, because I'm taking, I need to get across the room, but I'm taking tiny little steps. It takes me quite a long time to get there, right? This other extreme is I need to get across the room, but my steps are going across the parking lot. And they're getting rejected. And I go up to the other parking lot, I reject it. So it keeps throwing away my jumps. Right? So what you want, this is what you want, something in the middle. You want steps that are neither too big nor too small. That seems fine, but when you look at this again, the acceptance probability here is 87%, here is 31%, and here is 3%. Your instinct, or the instinct of most people, is to say, what do I want? Acceptance probability to be 87% or 30%. Well, I want 88. I don't want to be rejecting. That seems wasteful. I should go over 87%. If you look at what happens when you have a very high acceptance rate, that's actually not optimal. Is not high acceptance rates. Optimal is low correlation. Yeah, 0.96, 0.66, 0.98 for the correlations. Lag 1 correlation. We'll look at that a little bit more. So these are the same 3 chains. I just chopped off the burn-in. So, you know, this goes from 0 to 1500. This goes from 500 to 2000. I guess I ran, it's a little funny what I've done. There's still, I guess I ran a little longer as well. But I chopped, it's still to the 1500 draws, but not the first 500. The general rule is that you want an acceptance rate not like 100, but like 20% for vectors and 40% for scalars. And I'll show you where that comes from in a moment. This is another statistic that is quite actually useful in thinking about how these chains work and how to evaluate them. So again, I have this parameter psi. I've run capital M, say 5 chains. Each of them I run for 1,000 draws. So I have 5,000 draws altogether. My estimate at the end of the day is going to be, I'm just going to take the average of all 5,000, take the 5 chains, put them all in a pile, average them. That's my estimate. At stationarity, one thing I would like to know about is how much variability is this estimate? How much Monte Carlo variability is there? Maybe it's easier to look at this first. If I had independent draws, the variance of the average goes down as the sample size. So if I had an independent sample, the variance of that average would be, because I have 5,000 draws, would be the variance of the posterior variance divided by 5,000. Because I have correlated draws instead from a Markov chain, the formula is more complicated. It's this thing, this monster here. It still depends on the posterior variance, but instead of just having 1 over n plus 1 over nm, it has this thing that depends on all the lag correlations. So this is the lag, row 1 is lag 1 correlation, row 2 is lag 2 correlation, row 3 is lag 3 correlation. So the more big correlations you get, the bigger the variance is. So there's something that people we think of as it's the effective sample size, and you can think of that as maybe the effective independent sample size. So we know that with independence, the variance goes down by n over m. If they're not independent, it goes down according to this. How do these things relate, right? So, but the n effective is saying, if I have it's saying that for my sample, with the variance that I have, how big of an independent sample would I have needed to have the same level of information? So I can have a sample that's of size 10,000, but it has as much information as an independent sample of 100 because of the correlated sample. So the idea is to just kind of gauge how much information in a meaningful scale. So you're a scientist, right? You have some idea. If I want to learn about a mean and I have 1,000 draws, 1,000 replicates of that thing I'm trying to learn about, that's a pretty good sample. I should be able to say something. If I have a population of 1,000 people and ask them what they think about the new president, a sample size, an independent sample of the size of 1,000 is what that's on the order of things we use to predict elections, right? If you have a sample of 3 people, that's not very helpful, right? So what this thing is trying to do is to try to turn what looks like a huge amount of data, but it's not independent, into something that's a little bit more meaningful. Like it has as much information as an independent sample of size n, EF. Okay, so this is my normal 0, 1. I'm sorry. So I'm gonna simplify the problem a little bit. Instead of trying to do my power law analysis, I'm just trying to get a sample from normal 0, 1. And I have a jumping rule that is again normal, centered at the current value. And I want to say, what is the effect? And I run my chain. What is this? What is the sample size here? What is theta? Now, you obviously can't answer that, but I'm going to just run that same chain with four different levels of sigma and that result in 4 different probabilities and 4 different effective sample sizes. So you can see them all together here. Maybe more, they all have their own sample size and effective sample size and jumping rule. If you just look at those 4, which one do you think is the most has the highest effective sample size, has the most information? You can look at, which one has this one has the biggest jumping rule because it sticks the most. This one has the smallest jumping rule because it takes the smallest steps, and both of those lead to their own sort of correlation. So it's one of these two that's going to be optimal, and it's a little hard to tell. I made these plots some years ago, and so I looked at it this morning. I guessed and I got it right. It's this one that's the most informative. And you can see here the standard deviations, 1/4, 10, 3.5, and 1, and the effective sample size. This is a sample size of 1,000, but it has the information of 10. So you need 100 draws from this distribution to get as much information as one independent sample. So that's kind of pretty bad. That was not that much better, 20. 216, well, you've lost 3/4, but it's a lot better than the others, okay? And what this is meant to do is, it's important to make sure you have a big enough sample that say something meaningful. So the effective sample size is a way for you to kind of gauge the level of information that you have. Okay, so to pull this all together, lag 1 autocorrelation. So I did this for 4 different values of sigma that I show you here. I actually did it for like, I don't know, 100 values, maybe not 100. You can see it's kind of jumpy, but more than 4, a bunch of values. So for all of these values of sigma, I ran those chains in the way I had on the previous slide, and I computed the autocorrelation and just made a plot. And you can see the target in this case is normal 0, 1. So maybe not too surprisingly, 1 is what you want. You want to have a jumping rule that's about the size of the distribution. And a real problem, of course, you don't know the answer, but it turns out that that's the best autocorrelation. You can also plot, instead of plotting on the y-axis the autocorrelation, you can plot the effective sample size. And it's just essentially the thing turned upside down. The scale's not quite so, it's not just the reciprocal, but it's similar. That, the smallest autocorrelation corresponds to the biggest effective sample size. But what about the acceptance probabilities? Well, the acceptance probabilities don't work that way. If you have a very small standard deviation of the proposal, you have a very high acceptance rate. And as the standard deviation gets bigger, you have bigger and bigger jumps, you reject them. But if you put those two plots next to each other now, you want to maximize the effective sample size. I can't quite reach. Maybe I can do it with my pointer instead. Let me see that. So you want to be here. So what is the acceptance probability that you want? I'm not doing this very well at all. Maybe if I look here, just want to go across, and it's 0.4. So that target of 0.4 acceptance probability is not from doing this kind of calculation, but doing a mathematical calculation, but it turns out to be the same thing. The optimal acceptance probability is about 40% for a single parameter, and it goes down as the dimension gets higher. And the rule of thumb is about 20% if you have more than one parameter. Okay, so all of this is one dimension. Unfortunately, it becomes more complicated in any real problem where you have more than one dimension. Here's a posterior distribution for you. So the dotted line, the dots, the sample is my target posterior distribution, and the circles are a normal jumping rule. So if I have a very highly correlated distribution like this one, highly correlated, all the dots are nearly on a line, and I have a jumping rule like this, how do I make this jumping rule work, right? If I have a big standard deviation, I'm jumping left and right and up and down and missing the distribution and rejecting all the time. So I need to shrink this thing down to like maybe just the size of that little circle. Then I'm accepting, but it's going to take me a really long time to move up and down this distribution. So if you have highly correlated parameters, it's really hard to use just a regular kind of jumping rule that doesn't account for correlations. A better thing is something like this. If you can manage a posterior jumping rule that has the correlation in it, you have much, much better luck. This is 2 dimensions. Now, what happens when you have 5 dimensions or 100 dimensions or 1,000 dimensions? It gets quite tricky to set these things up. Here's another kind of posterior distribution. The reason this is a little bit of a funny posterior distribution, just made this up. The main point is that this kind of works because the correlation is the same everywhere. What I said doesn't quite make sense. The correlation is always the same everywhere because it's a property of the distribution. But the shape, the slope of this relationship is the same everywhere. So if I use a Gaussian distribution that has a particular correlation that corresponds to a particular slope, it kind of works. But if this thing becomes curved, especially if it becomes curved quite a lot, and I try to use a distribution like this, it becomes another level of difficulty, right? Because the shape of the distribution should be different in different parts of the parameter space. So that's quite awkward. Another thing to think about are scale. So this is again going back to this power law model. I pointed out these correlations are really big over here, and they kind of, it's not awful, but they don't ever quite get to 0. Why is that? This is, I showed you this Gaussian posterior distribution. And it looks beautiful, blah, blah, blah. What I've done here is I've plotted the alpha and the beta, or the X and Y axes on the same scale. So this is 0.2 and this is 0.05. So they're different scales. So here I've changed it. So this is 0.2 and this is 0.2. And what you can see is that the variability of one of those parameters, of the alpha parameter, the scale, is much bigger than the variability of beta. So if I use a round distribution like this, it's not really treating those parameters equally. So a new jumping rule is to use a different standard deviation for each alpha and beta. And I also, because you can, kind of hard to see it, it's pretty slight, but there's a small negative correlation here, as I use a jumping rule that accounts for that negative correlation as well. And when I do that, this is what the original jumping rule looked like for alpha, and the new one looks like this. So you can see that that's probably what the problem was, is that it's just jumping outside the distribution a little too much. The original effective sample size was 19 with a sample of size 500. So if we had computed the effective sample size originally, that would have been kind of a clue that something was not working quite well. The new effective sample size is 75. Well, not great, but I can run the chain instead of 500 iterations. I can run it a couple of thousand iterations. Okay, so this kind of a strategy, though, this stuff is tuned. Why did I pick standard deviations, different values, and a correlation not equal to 0? Because something about this posterior distribution. So what you can do is you can run your chain to get to be able to do this sort of a thing. I can run my chain with this sub-optimal sampler, maybe run it for 1,000 iterations, just get a little sense of what's going on. Compute the variance covariance matrix. So compute the variance of alpha, the variance of beta, the correlation, and then use that thing as the jumping variance for my proposal rule. So tune it to the problem without not working too hard at it, but just run it once, get a sense of what the problem looks like, update my proposal rule, and often things will work much, much better. So this slide here is kind of outlining that strategy. So you can see now this is has an M because it's a matrix, because I have more than one dimension. So use the variance covariance matrix from a standard fitted model for M. So if you can fit your model inside of a standard software package because you're doing some sort of spectral analysis, you might be able to just use the estimates that package spits out for the error bars. Use that for your standard deviations. Or there's adaptive methods, which are what I just described, which is run the chain a little bit and then estimate M. I'm pausing because I'm thinking of what I should say about K. So once I've set M, there's the K is a scalar. It's meant to, I can just multiply the variance by 2 or a half or 4 or a quarter. And usually what you're doing there is that's the point where you can tune, like it is at the bottom, to get the acceptance probabilities about right. It's going to be hard to get the acceptance probabilities right if the correlations are wrong, if the whole thing is just the parameters on very different scales or something. But once you have the general shape of the problem, you can just expand or contract the variance matrix and get the acceptance probability to work out. Transforming to normality. So I showed you this a while ago when you're using a normal approximation to these skewed distributions that might not work very well. Then I mentioned these transformations. So in this particular case, if I take the square root, instead of using theta, I use phi equal to the square root of theta. This looks much nicer. And if the posterior, I was saying yesterday, we were talking about statistical reasons why normal posterior distributions are easier. This is going to be much easier too. If my posterior distribution looks like a Gaussian, the Metropolis Hastings rules are all going to work much, much better as well. So there's a more skewed and a less skewed. This is the less skewed. This is the more skewed. So same thing. It doesn't look perfect, but it looks a lot better than that. So doing some rough investigations, taking some transformations, adjusting scales, all of that kind of thing to make the thing look kind of like a Gaussian distribution is a helpful strategy. This is just something about the kinds of transformations. The first thing to do is transforming to the real line. If it's strictly positive parameter, take the logarithm. If you have a parameter that's always between 0 and 1, take this transform. That takes it to the real line. If it's on the real line, it's more likely to look like Gaussian. It may not work. You should check it out, but that's the first line of defense. Sometimes the logarithm is too strong. Try the square root. What does too strong mean? You start with a parameter that is skewed, like say this one, and you take the logarithm, and then it's skewed the other way. So it's just as skewed, just the opposite problem. Take the square root instead. Still strictly positive, but at least it starts to look like a bell shape. Okay, so I'll leave that with you too, but that's just these are kind of rules of thumb that statisticians use generally when they want to make things look like Gaussian distributions, because the whole world is better when things look like a Gaussian. If you have strong correlations like this one, what might you do? Well, I described, there's different in strategies. One is that you can, what I said before is you can run it for a little while, compute the standard the variance covariance matrix and run with that. One problem with that is if you have a very highly, you suppose you start here, it's not going to move very far, right? It's just going to, it's going to take a long time before you can get all across the distribution and get a good estimate. So one thing you might do instead is, you see this kind of linear line, do a regression, figure out the slope of that line, and then, I have that y minus 3x. So, the slope of the line is 3. And so I replace y with this other thing, and it takes the variance and spreads it out. And now I have a very easy distribution to sample from. Similarly here, when you don't, it's not a linear relationship, but I do the same. If you do the same kind of trick, it's still not, it doesn't make it beautiful, but it spreads it out more. So it's going to be much easier to sample from this distribution than that distribution. Multiple modes are quite tricky. Imagine your posterior distribution looks like this. We talked about the scientific meaning. That's probably most important. Do not only focus on the biggest mode unless it's really, really big. It's 99% of the probability is probably fine. But if if these are 60, 20, 20, probably you want to keep track of the 20s as well. If they're challenging for any statistical method, everyone has to deal with these things, and it's a little problematic. Consider Metropolis Hastings. The problem with Metropolis Hastings, if you kind of are tuning, you have to be careful, right? If you're tuning your algorithm to this thing, you found, there's a mode over here, you compute the variance covariance, and you tune everything so it's sampling this thing lovely. You might never take a jump this big. The only thing we have is to take that chain, even though you tuned it here, start it all around the parameter space. Just give it a try. See if you end up accidentally landing on one of these other modes. You may never find them in a high dimensional space. It's true. It can be quite tricky to find them. So the value, that last thing is that value of excess dispersion and multiple starting values. So starting around the parameter space. Tune it to fit this thing, maybe again, just take the variance and double it. Just give yourself a chance to find something that's a little further away. Especially the real problem is, suppose this one has 95%, this one has 4%, and this one has 1%, and you somehow find this one, and you're happily sampling. You have beautiful autocorrelation, you can compute the variance standard deviations, but it's only 1%. So you have to be careful, and that's not really a Bayesian Monte Carlo Markov chain problem. It's just in big parameter spaces, it can be hard to find these things. Even optimizers have the same problem. There are methods. I don't want to go into it in any detail, but I do list some different methods that people use for that are specifically designed for multiple modes. Probably the best one and best known in astronomy, especially among cosmologists, it's called nested sampling. It's really designed to find those multiple modes. So it's something to keep in mind. Okay, so I'm trying to think about how to stop. We have maybe 7 more minutes. So I have something called the Gibbs sampler, and I have a little bit more extended examples. Which do I want to do? Well, how about if I think I'll do the Gibbs sampler and then. Okay, so what the Gibbs sampler does is it's another kind of Markov chain Monte Carlo. And it takes your parameter and divides it into 2 pieces. So instead of sampling theta 1 given y, you sample theta 1 given theta 2 and y, a conditional distribution of the posterior. And then you sample theta 2 given theta 1 and y. And this, together, the new value of theta 1 and theta 2 depend on the previous value. So it's another Markov chain, and it follows all the rules, so everything works lovely. And there's lots of cases where Gibbs samplers work quite nicely because these conditional distributions can be quite a bit easier to work with than the high dimensional ones. Now I'm going to go to it just because it's, to give you a full example can be quite tricky. So I'm going to give you just a simple example, which turns out to be exactly the problem we've been working on, which is this power law Poisson model. So this is the Poisson, this is the full posterior distribution. It's but it's the same as the likelihood because I used a flat prior. And so this is the Poisson distribution, e to the minus expectation of the Poisson, which is the power law, and then that expectation to the count law. And then you take a product over your multiple bins. So you can kind of rearrange those terms a little bit. But if you look at this thing as a function, alpha given beta and y, so I'm gonna find the conditional distribution of this thing, which means I just look at this thing as a function of alpha alone. Anything that doesn't involve alpha, like this stuff, I can just drop it because I'm just looking at the distribution of alpha. What I find is that's a gamma distribution. So I can just use a standard gamma distribution, just sample from that conditional distribution. For beta, now I drop everything that involves alpha, and I get another distribution, but this one's a kind of a complicated one because there's all these i's in there. It's not a standard, simple, clean distribution. I can't just pull the beta out. So this is not a standard distribution. But I can use this, I can use the grid method, or I could use Metropolis Hastings for that one parameter. And if I have Metropolis Hastings inside of a Gibbs sampler, that's also a Markov chain. And I get something called Metropolis within Gibbs, or I get something called Griddy Gibbs. We use the grid sampler for each of these conditional distributions. But it gives you another set of tools where you're working in smaller dimensions. The real advantage is you're working in a smaller dimensional parameter space. So it's a little easier to build these the algorithms to work well. When Gibbs samplers will work well or not work well. I'll leave some of that for you to kind of review on your own. And then I'm just going to finish. I'll leave that example for you as well. But go back to this example from the very, very beginning, where we do the stellar evolution. This was that model I had. Remember, this is the photometric magnitudes for each of the stars. This is the computer model that depends on the mass and the cluster parameters. And I showed you some of the posterior distributions that came up. One of the things that we did in this algorithm was to have a Metropolis Hastings update that was tuned on the fly to the parameter, to the shape of the posterior distribution. So you can see we use a series of preliminary runs that's used to evaluate and remove linear correlations. We tune a linear transformation to the correlations of the posterior distribution on the fly, and it results in dramatic improvements. I'm going to just show you kind of how it works in a toy and then show you the results in the real problem. So I was kind of talking about this earlier, right? I have this highly correlated posterior distribution, and I run it for a little while, but because it's so highly correlated, I don't move very far. I can't learn about the whole posterior distribution at all from this little sample, but I can learn something about just the slope. So I do a regression, and based on that regression, I decide to replace y with maybe alpha and beta is a good choice. I'm just doing a regression. That's nothing to do with the alpha and beta from that other problem, right? But so I replace y with I replace I replace y with z, which is y minus a minus bx. So I'm essentially, you're fitting a regression and you're looking at the residuals, the distance from the line, and that's the one, the up and down axis. And here, because now the correlation is essentially zero, I can run a Markov chain sampler very easily, and then I can then, once I have the sample, I can transform back to the original y, and I very quickly get across the parameter space. This is, again, this toy example looking at the autocorrelation functions and the time series plot. So this is what the Markov chain looks like on the original scale, and on the new scale, I'm only running at 50 iterations, but you can see it's jumping around a lot faster, essentially independent, high correlations. And then I think, this is the real problem. Yeah.
You have an autocorrelation function, and you were saying you want it to have small correlations relatively fast. Is it more important that falls below a certain threshold, or that it falls to a level where it goes positive and negative, fluctuating around zero?
The positive and negative. I'll just finish this out, and I'll go back to the example. Essentially done. So this is the real problem now. This is without doing the linear transformation. This is with the linear transformation. So this is again the time series plot. You can see they're running around much more quickly. So let me just see if I can find an example of an autocorrelation function. There's some. Yeah, so I mean, you don't really need it to be doing this sort of stuff. Once it's small enough, whether or not it's positive or negative, I don't even look at it. Usually you see this kind of wave pattern in there once it gets small, and I think, it's just essentially, you're looking at a time series with correlations in it. So when you compute these funny statistics, that those correlations are still there. What you really want, the other question to ask, this, it starts off, it's just falling off. If you really would like it to continue on that trajectory, it would have been fine. So this kind of behavior always worries me. Sometimes I remain worried and move on because I can't figure out how to get rid of it. But if it's relatively low, but still positive, it's troublesome, but not necessarily a death sentence. But what you really want is to get it so that just like you have this kind of pattern of small numbers that are, whatever it does, I don't worry about when it gets essentially the error bars. Right. Okay, so it's time to stop. That's all I have. Are there any final questions? So Axel has a question. We can see what at the
No,
thing.
it's more of a common
Yeah.
on the grid sampling. I just wanted to defend it.
Good. I like it. It's just, it's a little easy.
No, this was like two technical comments. So the first one is, I think, what's typically done also in practice, I mean, like with the normal sampling, you get kind of like the center of the pixel, or like
Yeah.
the center of the bin you have chosen. And then typically you would, for example, like randomize the grid within the pixel. And you can even use something like a triangular distribution, and then you get really relation.
Yeah, I mean,
It works in 1D. And then higher dimensions, I found this method. I mean, it's big, but what's nice about this is even in higher dimensions, I mean, the sums or the bins are uncorrelated. And then what you do in practice is you flatten those out still to like one-dimensional thing, then compute the inverse CDF. And then when searching the inverse CDF, you can actually use a binary search. And so this actually scales with the logarithm of the number of pixels.
yeah, there's some clever things people do.
Not too bad.
Yeah.
So I've used this method nicely, for example, like in 4 dimensions, for example, something like for example, the morphology of some source and the spectrum and the time at the same time.
So just to make sure everyone's on the same page, right, that I'm on the same page, you can instead of worrying about this kind of shape, you can just do it in the middle and make it a square. That makes it simpler.
Yes.
And if you have, the thing is that as soon as you have anything like this, it kind of doesn't matter, right? So it's maybe not worth worrying too much about the shapes that, but it depends on, sometimes it's your computing. If it takes quite a lot of power to compute at each grid point, then maybe you want to be careful about it, have fewer grid points, or you want to be more careful about geometry, or maybe it's just like worrying about the geometry or letting your computer run for an extra 4 microseconds. It's probably better to not worry about the geometry. But the more interesting thing, or that is quite clever, what Axel is describing, is you essentially take a high dimensional thing and you map it to 1 dimension. Tell me if that's right. And then you can work back with something in 1 dimension, and you can take it back to the higher dimension again. You kind of fold the parameter down to 1 dimension. Is that describing what you?
Yes, and in addition, to sample them from the multinomial distribution, you go via the inverse CCF.
Yeah.
And what's nice about this is that you can actually use, like from a computer science perspective, binary search, which
I see.
scales with the log of number.
Yeah. So when I do this stuff, I use a little canned routine to sample from multinomial distribution. That there may be more, either that canned routine is doing something more efficient,
Possibly, yeah.
or I could be more efficient by, not using the canned routine, so that you're just, how to sample from a multinomial distribution. There's more and less efficient ways to do that. Was there anyone on the?
Yeah, no.
Okay, well, it's time for lunch, I think. So thanks for your attention, and we'll resume
Next Friday.
Thursday,
Oh,
week from Thursday, yeah.
not this week.
No, yeah, we, like, 9 days.
Fine.